Here is a strange question. Does a hot cup of tea weigh more than the same cup after it cools? The answer is yes. The difference is far too small for a kitchen scale, but the hot cup contains more energy, and that extra energy adds a tiny amount to its mass. A charged battery also weighs slightly more than the same battery after it has been used. A compressed spring weighs slightly more than the same spring after it is released. These changes are incredibly small, but they point to one big idea. Energy inside a system contributes to the mass of that system. And soon we will weigh something smaller than an atom and find that some expected mass is missing. Nothing has vanished. Einstein's most famous equation will tell us where it went. Imagine a perfectly sealed box. Inside it is a charged battery and a lamp. We place the whole box on an impossibly accurate scale. The battery powers the lamp. Chemical energy becomes light and heat, but all of it remains trapped inside. Has the box become lighter? No. The energy changed form, but none left the box. Its total mass stays the same. Now open a tiny window and let some light escape. What should happen to the scale? It should fall by an unbelievably small amount. The box has lost energy, so it has also lost a corresponding amount of mass. First rule: before discussing mass and energy, decide what is inside the system and what has crossed its boundary. Now we can read the equation. E0 equals mc². E0 means the energy of the complete system when the system as a whole is not moving past us. This is its rest energy. M means the mass of that complete system. C is the speed of light. So, in ordinary language, the rest energy of a system equals its mass multiplied by the speed of light squared. The equation does not say that matter magically changes into another substance called energy. It says that the mass of a complete system and the energy inside it are connected. Because the speed of light squared is enormous, a tiny change in mass can represent a surprisingly large change in energy. Now let us test that with a real measurement. A proton and a neutron can join to form a deuteron, the nucleus of a type of hydrogen. Before the numbers, make a prediction. Should the joined deuteron weigh exactly as much as the proton and neutron added together? It does not. Separately, their combined mass is about 2.0159 atomic mass units. The deuteron's mass is about 2.0136 units. The joined nucleus is lighter by about 0.12%. This difference is called the mass defect. Defect does not mean the nucleus is faulty. It means there is a measurable gap between the separate particles and the bound nucleus. So where did the missing mass go? We need only 3 symbols. E0 is rest energy, the energy of the whole system in its resting viewpoint. M is the mass of the whole system. Physicists call it invariant mass. For now, remember, it belongs to the complete system. C is the speed of light, about 300 million meters per second. And the letter C is squared. That square makes the scale enormous. The units also fit. Kilograms multiplied by meters squared per second squared give joules, the everyday unit of energy. Matching units does not prove the equation, but it confirms that mass multiplied by c² has the right kind of unit to be energy. The full measured values will stay on screen. You do not need to memorize them. The mass difference is about 2.388 thousandths of an atomic mass unit. For atoms and particles, physicists often use the electron volt, a very small unit of energy. A visible light photon carries only a few electron volts. 1 mega electron volt is 1 million electron volts. Using E0 equals mc², the deuteron's mass gap becomes about 2.22 mega electron volts. In everyday units, that is far less than a trillionth of a joule. But it comes from one nucleus. It is roughly the energy carried by 1 million visible light photons from a system smaller than an atom. Do not memorize 2.22 mega electron volts. Remember the scale. Tiny in everyday life, enormous for one nucleus. Where did the missing mass go? When the proton and neutron join, the new bound system releases energy through radiation and motion. If that energy remains inside our system boundary, the mass of the complete system has not fallen. The energy is still included. But if it leaves, the deuteron left behind has less total energy than the separate particles had before. And because a system's mass reflects its rest energy, the deuteron has less mass. The 2.22 mega electron volts is called the binding energy. It is the energy we must put back in to separate the deuteron completely into a free proton and neutron. Binding energy is not extra glue adding weight. It measures how much lower the bound system's energy is than the energy of its separated parts. The speed of light squared makes small mass differences represent large energy differences. A mass difference of 1 microgram, far smaller than a grain of salt, corresponds to about 90 million joules. That is roughly enough energy to run a 1 kilowatt room heater for 25 hours. But this is not free energy. The equation tells us what a mass difference is worth in energy units. It does not tell us whether a process producing that difference is possible. Real reactions must obey other rules, including charge and momentum conservation. The equation gives the scale. The physical process decides what can happen. Which sentence is better? Sentence 1. Some mass disappeared. Or sentence 2. Energy left the system, so the mass of that system decreased. The second is safer. It tells us what the system was, what crossed its boundary, and why its mass changed. This is what people usually mean when they say mass became energy. But the careful version is not about two substances changing costumes. It is about one complete energy account. Change the energy inside the account, and the mass changes with it. Keep the energy inside the boundary, and it remains part of the complete system. There is one safety label on the famous equation. E0 equals mc² describes rest energy. It is not the complete formula for every moving object. Imagine switching on a flashlight while floating freely in space. The light moves forward. The flashlight receives a tiny push backward. That push shows that light carries momentum, motion with direction. Now the puzzle. A particle of light, a photon, has zero invariant mass. Does that mean it has zero energy? No. Light clearly carries energy. For moving objects and light, physicists use a longer relationship containing both momentum and mass. You do not need to calculate with it today. Its message is enough. In the resting viewpoint, the momentum part becomes zero. and the longer relationship reduces to E0 equals mc². The famous equation is exact, as long as we keep the words rest energy. You already understand the idea. Now attach 6 useful labels in 3 pairs. First pair: system and system boundary. The things we include and the line separating what stays from what leaves. Second pair: rest energy and invariant mass. The energy of the complete system in its resting viewpoint and the corresponding mass of that system. Third pair: mass defect and binding energy. The measured mass gap between separate parts and their bound form, and the energy connected with that gap. These are not 6 unrelated definitions, they are one story. Choose the system, track the energy, measure the mass difference. Here is something popular accounts often leave out. Einstein's paper from 1905 did not display the equation in exactly the familiar modern form. He imagined a body releasing light in opposite directions and showed that losing energy also reduced the body's mass by the energy divided by the speed of light squared. Later work placed that insight inside the fuller relationship between energy and momentum. Now here is the explanation you can give in conversation. A system's mass is connected to the energy it contains when considered as a whole. If energy leaves that system, its mass decreases by a corresponding amount. That is why a bound nucleus can weigh less than the particles used to form it. E0 equals mc² describes rest energy. For moving objects and light, momentum must also be included. That is the introductory meaning of mass-energy equivalence. Mass did not mysteriously disappear. The system changed. Energy moved, and the mass recorded that change. But if energy affects inertia, can it also affect the shape of space and time? That is the question behind Einstein's field equation. For more great equations opened in this way, subscribe to QuestionKind.